Hello everybody, my name is Weston Turner, and this is my final project presentation for modeling rotorcraft maneuvers using machine learning for Data 670. Here's a brief overview of what we'll discuss during this presentation. It's going to be a summary of the entire project. So we'll talk through the description, this data set description, different techniques, the results, applications and conclusions, areas for future work, lessons learned during the entire project, and then I will leave a space for questions. Just before we get started here, it's important to know that this project was requested by the FAA to basically take a look at some of time series data that they had and to detect different maneuvers in the data. There was a team of data scientists working on this project, all looking to classify different types of maneuvers inside that data. All the data is time series, and it comes from a specific database called the ROAR database, where all of the different simulator events and some live fly events go for analysis. So my particular aspect of the project was to analyze the rotorcraft maneuvers and be able to detect where in those maneuvers traffic patterns are occurring. If you don't know what a traffic pattern is, look on the right side of the screen there, and you can see a depiction of what a basic traffic pattern looks like. It's basically how an aircraft, rotorcraft, or a fixed-wing airplane maneuvers around a airfield. You can see there's different legs, and ends in a takeoff, and then downwind, base, and approach is basically the parts of that. The goal of identifying these traffic patterns is to basically use that as a starting place to increase automation both in and outside of the cockpit. Inside the cockpit for the pilots, and then outside of the cockpit for any air traffic controllers that might be able to look at specific data and try to have alerts at potential collision between aircraft. There's 4 main KPIs for the project. KPI 1 is what percentage of the data that is a TPN is correctly labeled. Number 2 is what's the false alarm rate. It's important to note that when you're dealing with aviation, false alarms are actually somewhat more degrading than false positives. Or sorry, when you get a false alarm, it can basically degrade a pilot's situational awareness. So it's important that rate is low. And then KPI 4 is how easily obtainable is the data. If we can't get the data easily, it can't be applied against a wide range of rotorcraft, so it's significant for the project. The third KPI was the computational requirements. That was actually dropped during this analysis because after the time series data was deconstructed, all of the different techniques used took a matter of seconds, so it really wasn't that important, so I dropped it for comparison's sake. Alluded to this a little bit, but the description of the data set we used is based upon simulated rotorcraft flights. There's tons of different flights in this database. I only looked at about 35, but there's probably in the order of hundreds of thousands of flights that could be analyzed. Every flight is recorded at 40 hertz approximately, so that's 40 times a second. That leads to 40,000 plus observations per flight. So just looking at the 35 flights that I looked at, that's about 2.2 million observations. So it's a lot of data to sort through. It's all time series, so observations occurring at a specific time. All those particular data points have about 108 specific features. And then I went through and I classified all these features based upon their difficulty to obtain and their usefulness. I did this with expert input and some of my own background in aviation. So difficulty obtained means how could we get these variables in real life if this is on an actual aircraft. So you can see on the right there is an example of a flight data recorder, and that's a very complex flight data recorder. It takes a lot of inputs and generates outputs for analysis. But a lot of rotorcraft don't have a very advanced flight data recorder. They just have basic instrumentation, which includes potentially, just a basic pitch, roll, yaw, accelerometers type stuff. That's fairly easy to get, but some of the more detailed flight data recordings are very difficult to get. So that's the difficulty obtained. And then usefulness, it's high, medium, low, none. Some of the variables are very good predictors of certain things, others are not. So I graded the usefulness based upon, again, expert input, and then updated that with R-squared values after running some basic models there. So the realistic, what we're really looking for is variables that are easy to obtain and are highly useful, with the goal of trying to get the least number of variables and the highest amount of usefulness to meet the objectives. After sorting through the variables, about 37 out of 108 of those features were useful. The others were not as useful. Without delving too much into the data, some of them were just would never be able to predict what we're looking for. Another important aspect of the data is that it wasn't directly labeled. It had to be labeled using flight logs. So flight logs are basically when the pilot post-flight goes and writes down what occurred during the flight, realizes it's a human input, could be slightly biased, or could contain some irregularities. So basically had to take these flight logs verbatim and log the certain time period stuff was occurring as a traffic pattern or not traffic pattern. So it's pretty time consuming, and potentially there's an area there for improvement that we'll talk to a little bit later. After we got the data, then it's important to correctly prepare this data. One thing to realize is that when you first look at the time series data, it looks like it's all complete. There's numbers in every column. There's really no missing data. There's a few variables that had all zeros, but those were easily removed because they were not important. But because this is a simulator, some little strange things happen every once in a while. Occasionally, the sim is paused. So after a pilot completes something, then they will pause the simulator to talk about it. You can see this in the data. It's reflected by how the time jumps in this two observations about 5 minutes. So when the time jumps there, sometimes the location of the airplane changes, sometimes it doesn't. But it's important to account for this when we're looking at the time series data, because obviously if we're comparing one observation to the next, a 5-minute jump could be a significant change. So there's some minute little changes I put in the algorithm to deal with those. There's also sometimes where the sim gets repositioned. So if they've completed an event, sometimes they'll reposition where the aircraft is in space, and that'll happen instantaneously. So you'll have a jump in position without a jump in time. And again, that could cause some issues. So you have to look for those places and then be able to account for that. I basically use some high-level filters to account for non-realistic physics types movements there. And if it couldn't happen, then it would just basically remove those data points. After we're able to clean up the data, now we use the sliding window method to reduce the time series data into 180-second chunks. I'll talk about why we used 180-second here in a second. But after we did that, then basically I used derived variables instead of previous values. There's a lot of different ways for deconstructing time series. Some of them use sliding means or using basically observations that contain previous values in different time intervals. I went with derived variables because I found it to be the most useful approach. So what is the sliding window method that I've been talking about? Basically, I took 180-second chunks of each time series data, and then I basically were able to extract certain variables out of that using derived variables or feature engineering. Because I was able to extract that data, I reduced the file size by a factor of 1,000, which is pretty significant, and it produces the ability to be able to real-time analyze the data that's coming from these sources. Some of the variables, like I said, are just derived. They have very simple transformations, basically taking that 180-second chunk, finding out the min, the max, standard deviation, the average. All those type of variables are recorded for simple transformations, and that happens on the majority of the features there. Others, I went a little bit further and used some feature engineering. So this is an example of a heading. What you can see here is that I'll take the heading in that time section and convert it into the start heading, the end heading. And then what we have is total heading change and relative heading change. So you can see on this first example, the start heading is north and the end heading is east. So the total heading change in that is 90 degrees. You can see this in the next example, the start heading is east and the end heading is east. But because the aircraft turns through north, the total heading change is actually 180 degrees. So you can see by just comparing the total heading change and the relative heading change, between the two examples there, you can learn a lot about what type of maneuvers might have occurred. So I'll do that with heading. I also did one for distance. More of that you can see in the report, but those are two examples of some derived variables that I used. After developing all of the derived variables, now it was time to get into the actual techniques to be able to analyze this data. Basically, I use a lot of iterations of different models. The first one I'll talk to is filtering. That one itself, basically the intent here is to be able to produce these derived variables that are good enough to be able to predict the actual maneuver. So without having any machine learning, just take the derived variables and try to predict. What I figured out here is that at least the ones that I created were not good enough to predict the target variable accurately. So you can see over here, I circled two in green, that if you take maximum altitude over a 180-second window, there's definitely areas, so blue is not traffic pattern, orange traffic pattern. There's definitely areas here in blue where just non-traffic patterns exist. So it's basically above about 1,600 feet maximum altitude. So there is a way to basically get rid of all those observations. And then you can see down here in standard deviation, altitude high, standard deviations also equate to mostly non-traffic patterns. Interestingly enough, for the relative turns, which is one of the best predictor variables, there are a lot of observations of low relative turn that occur with non-traffic patterns, but there's also some traffic patterns in there. So if we want to lose none of the traffic pattern data, then it's hard to filter out relative turn fairly well. So again, it's hard to use these filters just to isolate that target variable. What it can do though, and what I found really useful for the project, is to balance the target variable. So you can see on the right side of the screen here, sorry to bring up a pointer again, but there's a disproportionate amount of non-traffic patterns, 528, to traffic patterns, 212. If we apply the filters, we can basically bring that down to a 50-50 split, so balance that target variable, and I'll talk about how I use that in later models. So basically went through that. I talked to filtering here. I also use a artificial neural network and then decision trees. I used SAS-EM to compare all these models, and then I developed the final models using Python so I could tune them a little bit better and run them a little bit quicker. So for the results that we actually got out of all these models, I just captured a few of them here, the ones I wanted to talk about. I ran a little bit more of this, more details are in the report. So you can see with that model, the first one, the filtering, the best value I was able to get for KPI 1 is about 61%. I could get better values for KPI 1 if I was willing to accept some loss of some potential traffic pattern segments, but my going game plan was to not lose a lot of traffic patterns, so it produced a lower KPI 1 value. So you can see now we get into the model 3, 4, which are all artificial neural networks. These are all summarized by, they're grouped by the type of features that were used. So if I just used all the easy filters, all the easy features and didn't filter at all, that's model 3 Bravo, you can see that in most cases that actually met the requirements for the KPIs. The KPI 1 value is 90%, which is a little bit lower than I wanted, but it's still mostly meeting all the requirements there. Now if I take that similar technique and I apply a filter to it, so that means the filters were basically, again, like I talked to in the previous slide, to balance the target variable. Then, that's model 4 Bravo. You can see that that model has a KPI 1 value of 96% and KPI 2 at 3.92%, which is awesome. That meets all the requirements that I need, and it performs very well. KPI 1 threshold was about 94%. KPI 2 is about 5%. So it meets the requirements there. It's important to note, so I put a model 4C in here, which I didn't really do a thorough analysis on there, but basically I included both easy features and medium features. And again, that significantly improves the accuracy and all the other metrics. So there's a balance there between how many features you want to include, how many features are realistic, and what requirement you have for the accuracy. One thing that is very difficult to explain is that because we're deconstructing the time series and we have a sliding window, when we reconstruct the time series, some of those windows overlap. So if only a few percentage of those windows are mislabeled with the algorithm, it actually still might produce an overall result which leads to the correct label. So if they all overlap but only one of them is wrong, then 5 out of 6 still predict the correct amount. So what I found is as long as the overall KPI1 value is above about 94%, it leads to about 100% accuracy on correctly finding the traffic patterns in the data. So that's what that little bullet there means. Finally, the decision tree, which I would like to use if it worked well, did not produce good enough results. So it only had about 86%. It had very good accuracy, but again, the KPI1 value was only about 86%. Okay, so what are the key applications and conclusions of this work? The sliding window technique is very useful. It can basically extract a lot of information and be able to condense that. So you can use some pretty easy algorithms to be able to extract stuff, and it does it fairly quickly, which is great. The thing that you have to be careful of is you have to be able to experiment with different window and step sizes, which is probably where the most time is used in the actual computation, is finding what that is best. And I'll be honest that the times that may work for some maneuvers may not work for other maneuvers. So you may have to go through the data several times to develop different window sizes based upon what maneuvers you're trying to detect. Next is the feature engineering. So developing those complex features is great, extrapolating large amounts of useful data, but I need to explore more different types of variables to see if I can get better predictive capabilities. You can see on this graph on the right that if I just use the engineered variables that I came up with, it only has a KPI1 value of about 88%. If I combine that with the easy features, so easy and engineered features, now I reach that KPI1 threshold here, about 95%. So again, potentially developing more features would lead to better results. Another application here is that high level filtering is good at balancing the target variable, which increases the KPI1 and 2 values and produces better results. But the important part here is it also could be the first step in the data extraction. So if we develop those high level filters, we could set gates on what data gets extracted. So for instance, if we know the altitude's above a certain number and he couldn't be in a traffic pattern, then we could just not export that data to this algorithm. So we could save some time when the aircraft's above a certain altitude. That's just an example. And then the final one is that you can use a relatively simple model to get the requirements that you need. You just have to be able to have good techniques prior to using the model. So there's some very complex things that you can use to extract time series data. They all have fairly robust computational requirements. This was fairly easy, so it just depends on what your requirement is, but it's also good to have a good understanding of what you're trying to look for so you can extract those features and keep the computational requirements low. All right, so our future work overall, there's a lot of room for improvement, and there's a lot of other stuff that we can do with this project. The FAA has been working on this project for about 6 years. This is just a drop in the bucket for what we could potentially do. When I first started the project, I wanted to not only identify the traffic patterns, but I also wanted to look at creating the specific maneuvers. What I found is that there just wasn't enough time in this project to accomplish all that. The first step, though, in order to grade specific maneuvers is to get more data. And not only do we need more data, but we need to have labeled data. And that's the problem, because the data is there, it's just a lot of it's unlabeled, and a lot of the labels come from the flight log. So there needs to be a way to automate that process. My initial thoughts are potentially having someone else in the simulator while this is going on to basically write down all the times so they're more accurate, and potentially make that person the data analyst so they can take that data, go right into their algorithms and plug it in and quickly label the data, or come up with a more automated process to do that as well. After you figure that out and potentially grade the maneuvers, then it's good to have a way to implement that in simulators. So before you want to put anything in an actual aircraft, in flight. It's always a good idea to risk reduce it first in a simulator. Um, the great news is that all of these algorithms can be easily integrated into X-Plane, which is a simulator program. On the overlay on the right, you can see that I basically took X-Plane data and overlaid it with, I think this is just like wind data, but it's just a proof of concept. You can overlay that data and you can see where that's occurring. And so you could potentially take other features, overlay those in real time in X-Plane and get good data from that. After you're able to do that in a simulator, now you can go to live flight test. So this is still probably a couple of years down the road, but use of a smart co-pilot to produce, letting you know what type of maneuver you're currently doing and the grade of that maneuver might be useful, or some other type of display dashboard that has flight facts of the flight, or what you've done good and what you've done bad, for kind of a debrief there. I set a tablet display so you don't have to integrate it into the aircraft, and it's going to be something that you can bring into the aircraft, and that should save a little bit of time. Overall, there's lots of lessons that I learned while doing this project. The most important aspect of this project, and I would say all these projects by far, is getting a good understanding of the data first. Luckily, because of my background, I had a pretty decent understanding of what the data meant, but some people did not have as good of an understanding, and that led to using some features that weren't entirely useful or were reliable in the real world there. The next is you have to have a good preparation of the data, especially for time series data. It's important that once you get all that data prepared correctly, then using any technique is pretty trivial, just to plug it in there and get your results out. But properly preparing it is huge in time series. There's a lot of different methods to deal with the time series data, but a lot of them apply to like price forecasting, more specifically using it for financial analysis or stuff like that. So again, getting back to that data understanding, you got to know what you're dealing with to be able to know how to apply it. So developing this method, I think, worked well. As far as this specific class goes, I think you need to have a realistic scope. I saw some of the other students' work, I think a little bit overreaching sometimes, so we need to be careful of what we're able to commit to during this 3-month-long class. You need to have achievable goals, and so you can get a thorough and complete analysis on what you're actually doing. And then finally, I think for the overall course, a good data analyst is more than just the algorithms and visualizations they can produce. So just because you can run, a fancy Python algorithm or produce a great visualization that looks super cool, those are all, in my mind, technician jobs, stuff that we can do. Just pay a technician to produce something. But an analyst is somebody who puts everything together and is able to produce that in a logical and presentable form to management or to your boss or whoever you're presenting it to. So I think that's a big difference there. That's why we're writing all those reports, doing all these presentations, to get from that technician to becoming that analyst. So just something to think about. All right, and there are my references. And I'll open it up for questions. Obviously, if you guys have any questions, just email me or write it on the message board or write it in the comments here. All right, thanks for your time.